Hi everyone, can you hear me? I can't hear
Good
you.
evening, Sandeep. Good evening, Sandeep sir. How are you?
I'm good. How are you, Ranvi?
All good, sir. So far, going well.
I see. I see. Good, 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 good. All right. I understand कि अभी I've gone a little more into data structures algorithm. So how are you finding it so far?
So far, sir. See, point वही है. We are away from this programming and all for long and all, but trying to understand as much as possible. Uh, you know, um, Not 100%. To be very honest with you, we cannot say that 100%. We are there, but yes, maybe 50% at least. We can participate in solving the problem, right? Maybe
Hmm.
then somebody can write and we can also write. But I think that's how, and everybody objective is different, right? Keeping in a mind of 18 years, we already spoke to you. In industry last 18 years, what best we can do in delivery, program, project. I think that's what our forte, right?
Right.
So I
Right.
think that's how we are digesting the things and practicing something,
Right.
and we'll make sure all the data science related tool we know, we can hire the people, we can mentor the teams. I think that's what my objective and Chandra objective when we spoke to you.
Okay. 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 But yeah, are you doing some hands-on in the
Yeah,
course?
yeah, yeah. We whatever you covering, sir, we be
Okay.
doing.
Very
Yeah.
good. Very good.
At least not everything, but whatever you teaching us, we go and just write those code definitely
Okay. Very good.
in the lab.
Very good. And yeah, at the same time, are you guys finishing up? Are you guys finishing up the exercises in the course?
Yes, yes, yes.
Okay. Okay. All right. All right. Very good. Very good. And wonderful. Wonderful. Okay. And so last time we basically talked about binary search tree. Okay. And we will continue from there. And but there are a lot of things to cover. And what I'm thinking is that, see, we are going to cover basics of how to scrape the website, basics of things, right? So we should also, I would be covering something called sentiment analysis as part of Python course. Okay, that's something new that I'm doing. I've not done it before. Doing the sentiment analysis using the large language models, the one that you're seeing, by using the zero-shot learning. So it's like the last chapter is generative AI, and we are bringing some part of it in the first chapter. So don't get alarmed. It's pretty easy. Okay. And yeah, and okay. So yeah, one thing I would say, Ranbir, is that it's great that you are able to do hands-on. And my honest request to everyone in the class would be that instead of just thinking in terms of tool user, that there is a tool, we'll use it, start thinking like a tool builder. Okay. Why I say it is because people who start to think like a tool builder, they start to become very efficient users of a tool. They can
Mhm.
critically question a tool. You may not build a tool, but if you know and if you start thinking like a tool builder, you'll be able to critically question that are we using this tool rather than that tool? Can't we just patch it up and so on? Okay, and that's
Mhm.
a very, very, very important part. And as I was telling you last time, also in one of my projects, we had to compare. compare the annotations. So there is a tool called Label Studio. Okay. Now, as people are working in the AI industry, right? So what people are doing these days is, let me just check my mic is working or not. Okay, I'll just finish this. I hope I'm not repeating myself. Okay, so stop me if I'm repeating myself. So basically, so in this, what people usually do is they use this open source tool. Let's say tomorrow you are going to work on a machine learning or AI project. Okay, so what
Mhm.
people usually do is they use something called Label Studio. Okay, so it's an open source tool. Okay, and using this open source tool, the annotators, like basically whenever you're building a model, you will get the data annotated. If you don't have the data, you will get annotators and you'll start annotating, like giving an image. This here is a person, here is the like giving a car, this is the number plate. So you start to do the labeling. Okay. So say take a case of say Label Studio. Label Studio is as of today, most of the people are using Label Studio. There is a paid version of Label Studio where you can essentially just get those premium features. Now, in the project that I'm working right now, where we have hired lots of doctors and lots of nurses, and these doctors and nurses are basically labeling the documents. Okay, the way I wanted them to, give me the information, they are just going through these documents and giving me. Now, we realized that these doctors and nurses will make mistake while annotating the documents. So you have a text document like a doctor's report, and we mark it, okay, this is where we are talking about cancer, this is where we are talking about treatment. So we mark those rectangles in the text. Now, now we know that these annotators will make the mistake, okay? Um, and I hope everybody's getting so far what I'm talking about. Yeah. If you want,
Yep.
yeah, if there is a simple doubt, just stop me. Okay. So we have essentially a setup where it's an AI project. We are building a model around predicting something from the image. And what we've done is we have hired these annotators, or you can say nurses and doctors. Okay, we are not supposed to hire in India, so we have hired in US, and so it's a fairly costly affair. Now, what they do is they open the document, mark the document with a label. Like you see the rectangle, like this rectangle, they mark in the document and mark it. This is X, this is Y, whatever we configure, they mark it. Now, why I'm telling you this story is number one, most of the project that you'll do, you will end up doing annotations yourself. Okay. And annotation could be for multiple reasons. Number one, it could be for evaluating whether your model is working or not. And annotations could be for training your model. Sometimes you don't train the model, you just use off the shelf models and just evaluate the performance. Okay. So, but nevertheless, in many situations, in many of the projects, you might have to annotate the data. Okay. Like one of the projects I was doing was extracting questions from an image. Okay. So there also I needed annotations. And Label Studio has become like a de facto, right? Now, to make sure that annotators don't make a mistake, what we did was we gave same documents to multiple annotators, same document to multiple annotators, and we basically cross-checked if two annotators are agreeing. This is called inter-annotator agreement. So these are agreeing or not. Now, here's the important thing. When we thought, okay, we'll just compare one annotator versus another annotator, we realized that that feature is not there in Label Studio open source version. The feature is there in Label Studio enterprise version. to compare the one annotator versus another one. Okay. Now, the organization doesn't want to buy right now, or even if it wants to buy, it'll take a long time for purchase. Now, I cannot wait till the organization is going to purchase. So what we did was we exported all the labels from one side and we basically coded it up. Okay. Now, if we were not handy with coding it up, if my team was not handy with coding it up, the we would have been completely blocked in the project. Okay. So the thing that unblocks us here is number one, knowing that the JSON formatted data can be passed and we can just write our own code to read it and compare one JSON file versus another JSON file and list down everything. Okay. Second, first is knowing that that's possible. Second is that understanding the difficulty level of it and understanding the nitty-gritties of it is another very important aspect of knowing the programming. Okay. And third is, of course, coding it up. Okay. So all the three things, the aim for the reason why I walk you through data structures, coding is the purpose is that in a complex project, you keep your eyes on the end objective and don't get, become hopeless that O Level Studio is not providing, so we can't do this. And essentially, understanding coding, understanding what is possible, what is not, is something that gives you the ability to solve problems. Okay. So that's why I keep requesting everyone again and again to do coding and do coding with me and the algorithms. The most of these things are actually common sense. Okay. But it's difficult common sense. It's not that easy to. Okay. I remember very well when I did not know coding, my way of thinking was very different. Was very different. I remember very well.
Hi Sandeep.
Yes.
Actually, I want to know why we are doing like data labeling. Why it is important.
In my project.
Uh, yes, yes.
So basically, I want a data we call it golden data. Golden data means something that we can rely. And once you can rely on data, you can use that for evaluating whatever you're building, as well as you can use that data to train. Okay. So that's why we are labeling. Essentially, we have, let's say, reports by doctors. And given each report, we have to identify whether this report corresponds to cancer radiation or not. If it is, this report it's a scanned document, it's an image. If it is a, if it is a, if this doctor's report says that the person has undergone radiation, then what kind of radiation type it is, how much dose of radiation was given, and how many fractions, when did it start, when did it end. So we have to extract those variables. Okay. For that,
Sandeep,
I
how
want.
you were taking care, sorry to interrupt. Sandeep, how you were taking care of the sensitivity of the data actually? Like, because, these are the patient data. Normally, these are things, like for compliance reasons, you can't
Yeah.
open up the patient names and provide,
Yeah.
any of
Yeah.
the
Yeah.
details. And the compliances like you have to adhere to compliances like HIPAA and whatnot, running
Yeah.
in health
Yeah.
sectors and whatnot.
Yeah. Yeah. So good, very good question. Very good question. So there are like multiple levels of security. There's something called a compliance level called HIPAA. Okay, that HIPAA says that doctors and the companies who own the record have they can take a look at the people's records, and if they find it important for a contractor to be able to access these documents, they have to make sure the contractor is onboarded and contactor is educated and so on. So, and second, you cannot transfer these documents to the another continent. So they can't be transferred to India. So, and on top of it, what we usually do.
And I mean, I don't know the structure.
Hmm?
Yeah, sorry, Sandeep. I'm not sure like what's the structuring there in US or in Canada, but here in Australia, like if you want access to sensitive data, you need to get the certain level of security compliances. Like you should be
Yeah. So all the
negatively
team,
vetted by
the
or extensively
entire team I
before you
have,
access that.
entire team I have built, they have all gone through a lot of trainings on security. That's first thing. Second thing is we have separated two kinds of data. One that can be looked at by external people like me, and the other confidential reports that we can't see it. Okay. So the way my model is going to be first trained on less confidential data. And then once the model is trained on this and it's performing great, I'm going to hand it over to them and give them the entire of training process. So they will train it on larger data set, and then they will deploy it. Got it? So there are, I think the primary problem with most of these projects is the data compliance. Okay. And and that's one of the reasons why it is so hard to, provide a consulting in the AI domain, specifically in pharma, okay, medical domain,
Yep.
because of the compliance. Unless and until what you are offering, what your capability is irresistible to an organization, they want on board an external person. And that's why, like, I have been approached by as in very senior person from the company. Okay. And I mean, it's very difficult for anyone to convince that is it worth taking risk? Okay. Anyway,
Yep.
so yeah, it's pretty hard thing, and yeah, but the good part is that once you are and once I'm onboarded and one project is successful, then a lot of things open up, and that's why I've started, so I put two of my persons, one my previous course student, and one my teammate. I put two people into these projects, and I'm planning to put more as the time goes, and probably I'll hire more people on my payroll in India, and we'll be putting on such projects. There are quite a few projects that are done. So and yeah, but that doesn't mean that my classes will stop. My classes will continue. Okay. Uh, so I hope I answered your question.
Yep, Sandeep.
Okay. So yes, all right. Now, where are we? Okay. Let me just go to Google Drive. Do you mind if I pause for a moment? Okay. Oh, we have not opened the presentations for a very long time. All right. Okay. So we talked about something nice last time. Okay. Let me just take a look at this one. You guys can see my screen, everyone?
Yeah. Yes.
All right. So we talked about creating a tree. We created a binary search tree. Did anybody implement delete method yet? No?
No, Sandeep.
Sandeep,
In
I
particular,
tried.
me hadn't had a chance to speak to do anything. Yesterday was mayhem here because of that crowd strike thing.
Okay.
Yes, Sandeep, I try that, but little with help of the internet.
Okay, that's good. That's good. Show me.
Yeah, I share my screen.
Yes.
Just 1 minute.
It's completely okay. It's completely okay to use internet and do it. The most important aspect is to get the complete understanding of subject.
My screen is visible.
Yes.
Basically, I
Mm.
need the node basically. So basically, self is the our latest node.
Okay.
Then I call the return. Another method is the delete.
Okay.
Then check the value. This point I'm not understanding what is here. This one. Self dot delete dot node dot write dot successor dot value.
Mm.
Line number 64, I didn't understand what is happened because if I don't do that, then is the last pointer of the right or last pointer of the right not be deleted, just the pointer shifted to the upper node, which I want to swap that.
It's a recursive, right? It's a recursive.
Yeah.
Let's take
So,
did you follow any animation?
yeah, yesterday you told me na, this meeting, same thing. This one.
BST.
VST visualization. This one I follow
Mm.
that.
Yeah. So let's just take a look at this. Okay. So there is a recursive method of deletion or moving the tree. Okay. Right. Let's go there. Okay. So what's happening is there is a recursive thing that is happening, right? That's where you're right.
Yeah, yeah. Basically, left or right, I find out, then figure
Mm.
out is the left, what is the minimum of the left to left, then
Yeah. Yeah.
change to the node,
Right.
but
Right.
then I remove to the right node, and when I shift it to the left, then remove to the last right node. They automatically they conclude to the every node. So
Right.
that thing I follow the same like that. If example I follow that.
Hmm. Hmm. Okay.
This is one.
Just add one. Add. Yeah.
Yeah.
Okay.
Then
So now add say 3.
one more thing, 10. If I delete one,
Yeah, insert this.
yeah,
So see, what's going to happen is here, just add, let's say 5. Okay. All right. Okay. So see, now if you're going to delete, I'm going to zoom on your screen. Okay. So if you're going to delete this, oh, sorry, I'll just try to. I'm going to scribble on the screen. Okay. Why can't I scribble on the screen?
like if I delete the one node, the second node of the this tree,
Mhm. Yeah. Let's say what would happen if you delete one.
then 0 my is the parents node of the child,
Okay.
and the 10 is the 5 is the successive.
Wait. See, the parent node has to be bigger than the left, right?
Mhm.
Parent node has to be bigger than the node, and the right hand side has to be okay. Yeah, you're right. So let's take a look at say can you add say 3? Can you add say 3?
Yes.
Hmm. Okay. Yeah.
Yeah.
Now look at this. If you delete 10, what's going to happen?
If I delete the 10, then 5 become the parents
Yeah.
node, and
So
the
when you say
3.
5 becomes the parent node, right? So you have to delete 5. Okay. And
Okay.
then when 5 deletes, then what happens? Who takes the place of 5? 3 takes the
3,
place of 5.
3.
So that's what. Just try deleting, say 10. Yeah. So it starts at the top, searches for 10. It found the 10. Yeah. Okay. Now 5 went up. Okay. 5 became the parent, and that's it.
Yeah, we shifted to the node upper world, right?
Correct.
Yeah, that thing. Yeah, this I little bit confused.
All right. Let's say you put one, insert one.
One already. It's the left of the three.
Left. Oh, left. Okay. And zero. Can you put zero? I'm just trying to see if we can. Is everybody okay with the insert? Now, if you try deleting one, so what will happen? First, one will move up, then zero will move there. Okay, let's see. Just delete one. Okay. See, one. Yeah.
That thing is little bit confusing.
See what happened was, okay, let's pay attention. So here, see what happened was, so, okay, yeah, where is that? How do I write? Okay, I need to change something. I'm not able to scribble mode.
Like I face problem when like any node have left or right child. So figure out find the minimum value. If I delete the node, then shift it to the minimum value to the become as a node.
Mhm. Yeah. So
That thing I figure.
it's
Yeah.
an important part, right? Okay.
Yeah.
So let's say, how do I? Why am I not able to scribble today? Okay. Um, what do I read? Share screen, chat, start video, share whiteboards. Okay. Have we changed something on this thing? Wait. And yeah, I'm not able to. Okay, let's see. Pause, whiteboards, new whiteboard, existing, reset to default captions. What? Man. Don't tell me they changed it. Okay. Just give me a moment. I'll try sharing my screen and then. Okay.
Yeah.
Now I can annotate. Okay. And here also I can annotate. Can you try sharing your screen now?
Yes.
Okay. Just. Woohoo. I'm not able to scribble on your screen, dude. Okay. Anyway, I'll just take a screenshot and then do it. Okay. You switch once to the binary one and then
Binary code or visualization?
visualization. Okay. Then we'll come back here. All right. Okay. And for some reason, I'm not able to, when you are presenting, when I'm presenting, I'm able to scribble from my another login also. Okay. So I'll just try this. Okay. And it must be somewhere here. Yeah, this is how it looks to me. Okay. And go to full screen mode. Okay. So if you see here, right?
Just better you can open this website and
Yeah, that is better.
uh,
That's easier for me.
yeah, easier.
Okay. Yeah, yeah, it's unnecessarily confusing. Okay. Some university website, right? Yeah. Every time I find a better version. Okay. So let's say we put 50 and then we have 40, okay, 40, and we have, let's say, 51, okay, or let's say 75, okay. So this is a binary tree, okay. You can see here that this value is smaller, this value is larger, correct? So if this value get deleted, right, what are the options we have? Okay, we can, right, when let's say this is 50, 50 is having 40 this side and 75 this side. Okay, now if we delete 50, we have what all options we have? One is we make 75 as the parent and 40 as the left child, correct? And what other option we have? Other option is we make 40 as the parent and right is 75. We have both options, correct?
But which one is correct?
Both are correct.
Okay, because this website follow this like the
Yeah.
left is minimum is the parent and the right go bigger size, bigger node go to the right.
Right.
But I see multiple website he follow the different one. Big one go to the node and
Yeah.
the minimum value go to the left.
Correct. 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 So the
So
strategy.
this is not only very hard rule ki which one become as a node.
How many with these nodes? How many these three nodes? How many total binary trees can you make? Binary BST can you make? Binary search trees.
3 binary if I
Okay. So one is this method. What is the definition of binary search? The parent, the left child can be equal or small, and the right child has to be bigger than the right. Correct? So we could make the first another tree with 75 at the parent node. Okay. The left hand side could be 50 and 50, right? Now also here 75 as the parent node and left hand side 40 and right hand side 50. Correct. Now
3.
similarly for these and this also. Correct.
Yeah.
We will have like many permutations. So there are many possible trees are possible. Like if we delete, let's say 50. So either we can say 75 left node 40 or we can say 40 right node 75. Okay. Basically, what is the purpose of binary search tree? Binary search tree's purpose is we keep our data organized such that we can insert the data in between and extract the data quickly. Okay. We saw that when we do a normal binary search, we can just keep on going to the right or left, depending upon whether the midpoint is bigger or smaller. So in case of binary search, normally normal binary search, we had to sort our data. But when we keep the data sorted as a list, the problem is inserting the values was hard. So what people figured out, they made it like a tree instead of a list, and they keep on inserting values here and there. Okay. So either of the technique where we delete, say 50, okay. Let's say we have another value called 78. Okay. Why insertion?
You put in the delete.
Okay. So 78. And now let's say we have, okay. So we have, say, 60. Okay. Right. So you can see now if I delete, say, 50 here, what should happen? Okay. If I delete 50, either 40 will come here or 70 will, that's it, right? So if we delete 50, there are, what are our options? One is we make 40 at the top and 75 remains as it, and 60 and 78. Okay. That's if I delete 50, right? The other thing could be we move this up. Okay. So it becomes 75 and then 40. And then when you are deleting this value, one of the values need to go up, correct? So again, let's say we follow the strategy of deletion that bring the right side up. Okay, if right side exists, bring it up. If it doesn't exist, like move the left hand side. Okay. So we could do anything. We could it's like both algorithms are okay. So now if we move this here, this will become empty. Now to delete this, we'll have to move this one. So this will become 75 and this will become 78 and then will become 50. Okay. So let's see what happens. We are going to delete 50. Okay. Right? This was easy, correct? Now, can I, okay, this was easy because we basically deleted we basically moved the left side up, okay? Now, if we are going to move the left side up, let's see if we can have 30, let's say 30, okay? If we say 30, insert, okay, we added 30. Now we also added, let's say, 15, okay, and we also added, let's say, what do you say, 35, okay, and 35, okay. Okay, now let's say I add some more nodes to this one. What should I do? I'll just add 10. Okay, 10 will keep on going to the left, and there we have. And then let's say we also added something between 15 and 30. Okay, let's say 20. Okay, so you can see now. Now, if we are going to delete 40, it has two choices. One is move this or this. But its strategy is to move the left-hand side first. Let's see what happens. Okay, let's say we are deleting 40. Okay, let's say we are deleting 40. Okay, let's see what happens. You see, basically what it did was it kept on going to the right. Okay, it kept on going to the, it went left and tried to find the node that can swap. So if a children has a right-hand side node, it'll pick up that one and then swap it. Okay. Now let's take a look at what happens again if I say delete 35. Okay. So delete 35 will go to the left, try to search a node bigger than 35. We're all right. If you delete 35 here, right, any node bigger than 30 should come here. Okay. If that node is not found, then it'll move this one up. Let's see. We are going to right, we are going to delete 35. Okay, and yeah, let's see what happens. So if we delete 35, what will happen? Delete 35, it has got left node and there is nothing right node, so there is nothing on the left hand side which is smaller than 75 but bigger than 30, correct? So it will pick up from the right hand side. Let's see what happens. Delete 35.
Left side.
Yeah. Okay.
This website algorithm picking for the only for the left side, not goes for the right side.
Yeah. No, when there is nothing on the left hand side, then it picks up from right.
And then it's pick. Yeah. If left side is empty, then it will.
Yeah.
Sandeep, in that case, we need to have 60 as the root node, right?
It was anything. It can be anything. Let's see what happens now. So if basically if you delete 30, 15 is also a good candidate to go at the top. Okay.
But
20 will
pick
come.
the 20 will come.
Yeah, 20 will come. Sorry.
Yeah.
Okay. The max from the right hand side
Right.
will max from the left hand side will come up. Okay. All right. Yes. Max from the right-hand side will come up. And if you delete 20 now, who will come up? The max from left-hand side
15.
15 will come
Yeah,
up.
15.
Okay. 15 came up. Now, if you delete 15 again,
Then 10.
10 will come up. Okay. Right. 10 came up. Now, if you delete 10, it'll
Now
basically bring up the right-hand side up. Okay.
and 78.
Okay. No, it should bring in 60 because all the values on the right-hand side need to be bigger than this node at the top. So it'll now try to bring in the smallest value on the right-hand side.
Minimum.
Yeah. Okay. Let's say I delete 10. Oh, no, it's actually what it did was, yeah, it is still is a valid thing. So if the right node just gets swapped with the parent, it's okay. If there's nothing on the left-hand side. If there's nothing on the left-hand side, it's okay to just make the right-hand side as a parent. Because there is nothing on the right, this thing.
Yeah, no dot right, yes.
Okay. So yeah. So the strategy is simple. If there is a left node, try finding the biggest value on the left-hand side and replace it with the current the current node to be deleted. Okay. So the strategy is first of all, find the node that you're looking for. When we, let's say delete 75, it's going to search for 75. And once it has found the 75, then it'll go towards the left, okay, and try to find a node that is the maximum value, and then pick that node and swap it with the parent. Okay. And and if let's say, let's try to insert more values to it, okay? Or let me just delete it. So if let's say we have 66, let's say 70. If we insert 70, what will happen? So 70 will come here. Okay. Now if 75 is deleted, 70 will take its place, correct? Okay. Now let's add more nodes to 70 as a children. How will we add more nodes to this one? Let's say 65. I'm saying 65, insert. So now when we try to find the biggest node on the left-hand side, 70 will come up, right? When 70 goes up, who will take the place of 70? This node, correct? 65. Okay. Let's say now let's say how much let's say 65 bigger than 65 here. Let's say 68 I'm inserting here. Okay. All right. Okay. So now if I delete 75, what should happen? This guy is taking from the left-hand side. First, it'll try to find the biggest node on the left-hand side, and then delete that node. Okay, delete that node, and let's see how it goes. Okay, so I'm going to delete, what is that? I'm going to delete, say, 75. All right, so it's deleting that. Sorry, I inserted it instead of deleting it. Let's say I'm deleting 75, okay? Now, went up, 70 went up, and then again, that swap happened. It became, yeah. Now, I'm just thinking that what else could happen? Okay. If you are deleting a node, just move up. Oh, okay. Yeah. All right. So basically, if I delete, let's say 70 now, it will try to find this one and move it here, right? And let's say now we have 67. 67 will be here, right? Now, if I delete 70, 68 is the maximum on the left-hand side. So that will go up here. Okay. When that goes up, this one will become the parent. Okay. This one, when that goes up, this one will become the parent, and then let's say I have 69 here. Okay, I'm inserting 69, so 69 should come here. Okay, so this is a binary search tree. Okay. And when we put value, any node in this, they're basically going to. Now, if I delete, say 70, okay, this will go up, okay, and this will become the parent. Okay, let's say I'm deleting 70. Okay, let's say deleting 70. Okay. Oh, 69 was highest. Okay, 69 was highest. So it basically just picked it and went up. Now, if I say delete again, 69, it will try finding things from the left-hand side. Yeah. You see, this one got swapped. This became the parent node. All right. I hope I'm making sense. No. All right. Let's say 66 I insert twice. Okay. And 66. Right. Okay. Now, see, basically, if I delete, what's the biggest value in this? 67, correct? If I delete 68, 67 will be, 67 will become the root node. This would come here. So basically, this will start pointing to this one. Okay. Its left will become this value. Okay. So, yeah, you saw it? The next became the left value of that. Okay. All right. I hope I'm making sense right now. All right. Okay. Now you can share your code. I can walk through again.
Okay. My screen visible?
Yeah.
Basically, here okay. I will go through that first.
Okay. So basically, when we say delete, right? Somebody is calling your method delete, right? You are internally calling this method called self delete.
Underscore delete.
Is this code working? You tested it?
Yeah.
Okay.
This is working.
Okay.
But this is basically pick the rightmost is the bigger element and become as a node. Then
I see.
again separate.
Yeah. So either one you can do. Either you can swap with the left node or the right node.
But I didn't understand this like the how to remove the last element. Suppose I remove the one. Now then 10 become my root node right now.
Yeah.
And 0 shifted to the left. Then how to remove is the 10 or just swapping the I don't
What
see
do
the
you? This is your tree. Okay. This is just let me know that. Yeah. Yeah. Go ahead.
yeah. Suppose this is I want to delete like number 1 and then they replace to the number 10 and 0
Okay.
becomes the left node. But how to remove this right element if the one of the right is the 10 element? It's just swiping. I didn't see any the swiping code here. That's
No.
why I
Again. He is calling the same method called delete.
okay. But how to delete the 10? That is the point.
Huh? So,
Like who one
so-
delete the node 10?
okay. Wait. I'll just show you this. So basically, we are just changing the pointers. That's all. Okay. That's what I'm saying. Let's just read through the code. We're just changing the pointer. We are not really deleting it. Okay. So this code is working. This is from internet or is yours?
Little bit this else part I figure out in the internet. This part I figure out.
Let's read through the code and then see to poke hole in it. Okay. Let's go slowly and read through it. If node is not there, if node is blank, return blank. Right? If not node means if node is null, none, return none. None means nothing is there.
Nothing.
Okay. If value is equal to node dot value, which means we have found this node which needs to be deleted. Okay. Now basically what is happening is you have, so deletion means return the next substituted value. Okay. Deletion here means return the node which needs to be designated at this place. Okay. If you see, you are returning node, correct? And if you
Correct.
go up, go up. Yeah. Notice your line number 42.
Yeah.
Okay. So what you do, what delete method is doing? Delete method is basically searching for a node that needs to be replaced here. And then you're saying self.node is equal to self.delete.
Well, yeah.
So delete method finds the node who becomes the next successor to this node, the one who becomes the position holder, and we assign that to the self.node. Got it?
Good. Yeah.
Now, now here. So if the value is equal to node.value, that means we reached a place where the value is there. Okay. Now, if node.left, okay, neither there is left nor there is right. Okay. That means the whole tree has been deleted and we return none. Correct?
Yeah.
Now, if there is no such thing called nodes.left, meaning nothing on the left hand side, make the position right hand side one to be the position holder.
Yeah.
Correct? So we are returning node.right. Now, next one, if, right? Now, else if, okay. So if
Again.
so your logic is right biased. Okay.
Yeah.
Okay. Your logic is right. So what you're doing is if, okay, so if node.left does not exist, okay, which means you just return the whatever is on the right hand side. Okay. Now, right. So first case you handled where neither left is there nor right is there. Okay. In that case, you're returning empty. Now, second case is when your left is empty, so you are returning the right.
Right.
Okay. Now, if your right is empty, what to do?
Return left.
Okay. Now, if right is empty, then you return left. Now,
Left.
yeah. Now, let's say you have basically, if it is very clear that there is only one side, either left or right, then you are able to take a decision very clearly. Or if nothing is there or only one
Left.
side is there, you are just able to take the decision. Now is a situation where
Both.
you have both left and right both.
Yeah.
What to do in that case? Okay, so you are saying from the left hand side, from the right hand side, find the minimum. Okay, that's your successor.
Yeah.
Okay. Now, what you do is basically you call the same method called say this one. Okay. And repeat the process. Get the successor. Got it?
Got
You
it.
are
Yeah.
trying to find the successor and replace that with the at a position called right, and that's it. But you have to also return some value here in else. Correct? You got it?
Yeah. Also, I return that this node dot value is the successor dot value.
Okay.
So that's why the successor value replaced with the node value,
Hmm.
and then right we will the remove. That's why is the 10 is the remove from the right side.
Yeah.
Yeah.
You got it. So
Yeah.
basically just doing that.
Yeah.
Okay.
Then this is the different case was value is not like the bigger than the left side or right side. Then the again call the same delete method. So this
Yes.
recursively calling the everything. So I try that because first time try that, then set as a none value, not replace, not deleting the last value. So this thing I
Yeah.
try.
Okay. All right. Wonderful. If this is not found, then you return none. That means it cannot be deleted.
Yeah.
Okay. And perfect. I hope this is making sense to everyone. And I think everybody should try to code it. This is a good exercise, very good exercise. Though in normal life, if we see things, we can just swap them very easily and all of that, we can easily understand it. It's just that in code, it becomes a little confusing. So you have to just become conversant with walking through that.
Swiping, we need to swiping as well as deleting the last element of the reducing the size of the tree. That is the difficult part of from
Yeah, yeah, yeah. All right. Okay. So that was a binary search tree. Okay. Those who are very inclined in it. Okay. So you can, right? So, right. That was binary search tree. When do we, when do you can see my screen, right?
Yeah.
Right. When do you, okay. So let me ask you, when do you use binary search quickly? Normal binary search. Everyone?
Sorted list.
Yeah?
Sorted list.
Yes. Yes. If you have a list that is sorted and you have to keep,
Insert.
you have to, right? List is mostly read only. It's already sorted and you don't insert often. Okay? Because inserting into a list is a very painful affair. Okay? All right. So, yeah. And right. And when do you use binary search tree? We talked about this last time.
With the unsorted list, or we can say
Right. When
array.
uh, or you can say when you have like if you basically have some data, okay, right? Or you can say if you have static data and you have to keep searching multiple times. You have to search multiple times. You have to search multiple times. Okay, because binary search makes it faster to search and therefore. Now moving ahead. So when do you use binary search tree? Okay. When do you use binary search tree? Okay. Binary when insertions and deletions are happening very frequently, very frequently. Okay. One more thing to note that every programming language provides you these data structures so you can use them. Okay. You may not need to do this very often. Mostly all of these things are already available as per library. So it's important to know when to use which one. And these are pretty efficient things. Okay. So when you use binary search tree, when insertions and deletions are happening, okay, and why not dictionary? Usually, in most of your businesses, you can get everything done by dictionary. Okay, most of the work can be done quickly by dictionary, uh, right? When too much memory is not available. Okay, because dictionary takes decent amount of memory. Okay, so yes. All right. Now, so we talked about binary search tree. Okay.
And then one question.
Yes.
How does BST take less memory than dictionary? I mean, it will keep the same amount of information, right?
So what happens in case of dictionary, right? When you put something like let's say Sandeep, okay, equals right? When let's say this is my dictionary, okay, this is my dictionary, correct? And I'm putting Sandeep equal 10. Okay, this is my dictionary. All right. Let me just change this to code. Okay, so if you see, right, what actually happened inside this one, right? So what it does is it allocates a big array. Okay, big array gives, right, converts this string into a number. Okay, into a number. Let's say this got converted into 1,000. So it has already allocated, say, a million, and it has created, inside it has created a big list with, say, a million values in it. Of course, they are right now empty, but the space has been allocated. Okay. And when you say a Sandeep, it converts this into 1,000, goes to the thousandth position and puts Sandeep here. Okay. So at thousandth position. Okay. Now it says a, and it says, let's say, Dushyant. Okay. Now the way you converted this Sandeep into 1,000, right? That algorithm ended up converting this also to 1,000. Imagine, because there's let's see, whatever logic you wrote, like there is a simple logic of converting these digits into numbers by, say, uh, take the ASCII value of S, multiplied with 32, add A, then multiply that with 32, add N, and then keep on doing that and do some percentage 32. Not 32, percentage, say, a million. So that way you basically can convert this by adding up or doing some calculation on these letters and come up with the some number representation. And in this array, you go to that position and put Sandeep in there. Similarly, Dushyant, let's say this one is 1100, so it'll go to 1100 position in this dictionary, in this list, and we'll put Dushyant there. If there is a collision, then what it does is it creates a list of lists and puts multiple values into that position. So if you notice, it ends up allocating the whole array is very often. Okay, so though there are clever strategies, the memory has been optimized a lot in case of dictionary, but still, dictionary takes a lot of memory. Okay, so even if there are few elements, it will end up taking a lot of memory.
Okay. It's because the way it is structured. Okay.
Yeah,
Yes.
because internally it has created a blank list of elements, so that when you put key as a string, it converts the key into a number, goes to that location, and puts the text. Okay, so essentially this is built on top of a list. Okay, now I hope this makes sense to everybody. Now, dictionary takes too much memory. And right, so one of the problems that you would notice in case of binary search tree, right? After a while, okay, imagine you are inserting the values like in an order. Okay, let's see what happens if we insert values in a certain order. Okay, let's say I insert 1, insert 2, insert 3, insert 4, insert 5, insert 6, insert 7. Now notice this very carefully. Now insertion is taking so much time. What is the order of insertion? When I'm inserting 8, what is the order? Can somebody tell? It's not O log n. Earlier it was O log n, but if you are inserting the data in sequence, it is order of n. You see the bug in binary search tree? So if you give it a pre-ordered data, it would end up becoming linear search.
Right.
Right?
That means sorted data not work for the VHD.
Yes. Okay. It becomes so slow.
Yeah.
because height of the tree is equal to total number of elements now. So to traverse it, it has to keep hopping from one end to another. So it's like becomes super slow. Got it? Now, this is a big tragedy of binary search tree. Okay, that's where a lot of strategies came in. Okay, some of the strategies are called red black trees. Okay, and then AVL trees. Okay, so those who are interested, they can take a look at these things. Okay, and that's about it. All right. So everyone, those who are inclined, okay, right? So since the binary BST is prone to right prone to linear search, okay, or right, prone to imbalance, multiple strategies have come for for this. Okay, so essentially, these strategies basically do all sorts of magic in terms of you know, let's say red black trees. Okay, and visualization. You will see that interesting part. Okay, so you can insert 1, 2, okay, 3, okay. Now it balanced it quickly, right? So it balanced it. It moved true to the center. Okay, 4. Okay, 5. 6 is somehow like keeping a track of counts and then swapping them. Okay, it's just keeping a track that if there is a, you can see. All right. Okay. Right. So you can see, right. So nice. Okay. So you can see that it is basically node and the parent both are no red. Node is right child. Basically, it keeps on marking them red and black based on previous and so on, and then it just does that. Okay. So yeah. So it keeps on balancing it so that the tree becomes balanced. So searching becomes logarithmic, becomes extremely fast. Okay. So so basically to solve that bug in binary search tree, people came up with AVL tree, red black tree, and so on. Okay. So you can take a look. It's important to just know and understand the strategy. You may not be able to code it quickly. Nobody's going to ask you to code it quickly. In an interview, nobody's going to ask you to do that. Okay. Just that you should know how to deal with it. Okay. Now, the other question comes is in case of binary search tree. Okay. Another question comes in that what if my data does not fit in the memory? Okay. What if my data does not fit in the memory? Correct. Like this whole data, right? Okay. No, it's just looking for 7,7. Can I clear it? Is there a way to clear it? Okay. So never mind. I'll just, okay. So if your data is not fitting in the memory, okay, if your data is not fitting in the memory, what to do? Okay, in those cases, what it does is it basically all right, if your data is not fitting in the memory, so one of the strategy is the nodes at the top, let's say top 10 label, it'll keep in the memory. The rest of the nodes below, it'll keep in the disk. Okay, so essentially, this kind of makes it easy to just look at the top and so on. So in that case, people use something called B trees or B plus trees. Okay, you can take a look at those. I'm not going to jump deep dive into that. All right. Okay. So if your data does not fit in the memory, you use B tree or B plus trees. Okay. Now comes next very important thing. We call that, okay, it is called min heap. Okay, let's take a case of a very important thing. Question is, you need to build a scheduler, okay, right? And the way it works, this scheduler, the way it works is, okay, it finds the task which is of a smallest date time. Okay, smallest means like earliest. Okay, you can also read it like earliest. Okay, earliest. Okay, so what you want to build is you want to build a scheduler. Okay, what it does is it looks at all the jobs, finds the smallest, like the task to be done earliest, and then it basically executes it, removes it, and then keeps on repeating the process. Okay, it finds the next task that is the earliest, and then you basically do that, right? So here you basically want to build such that it should be extremely fast. Okay, the tasks keep on coming, new tasks keep on coming all the time, and you have to just pick the smallest value. Okay, so you can build it using binary search, correct, everybody? If you have to build a scheduler which basically picks the earliest task, so you have, let's say, hundreds of tasks coming in, you keep on inserting the task in the tree whenever they are coming in, and it basically checks it basically checks if the next task, the smallest earliest task, is smaller than current time, it picks it and then executes it. Otherwise it goes for sleep for that difference. Okay, and basically that's the role of a scheduler. When you think about schedulers in Unix, okay, right, in Unix there is a scheduler called cron, and then you have calendars. Okay, they all work on this principle. Okay, so they all work on this principle where they pick the task and they pick the next smallest task. If the smallest task is still 10 minutes later, it goes to sleep for 10 minutes, wakes up, checks the smallest task, and then picks it and then executes it. Okay, so it finds the task which is smallest date and time, and that's about it. Is everybody clear about this one? So
Um, Sorry, Sandeep. Quick question. I mean, the way a scheduler works, right? It looks at looks for a task based on the start time, right? Which has to be smallest. And why do we need a tree for it? Shouldn't it be a queue rather than a tree?
yeah, but the sequence in which the task comes in, not necessarily it will all the task that is coming in the last would always be the oldest, right? You might schedule the task which is of, let's say the situation could be, right, First task one, okay, execute at 1 p.m. Okay, the okay, the task two, okay, task two. This is task one. Task one. Task two could be execute at 12:30 p.m. Correct. Task three could be like start time could be at say 2 p.m. and task three could be 11 a.m. Okay, today itself. I mean, if it is a fresh new day.
Okay, got it.
Got
Got
it?
it. Yeah.
So queue may not work.
Okay.
But sir,
But
okay, Sumit, carry on.
So the
yeah,
tasks will
so
keep on coming. Tasks will keep
yeah,
on coming. People will keep on adding tasks.
so when we create a tree, right, what will be the pivot be? I mean, the root be. How will we choose a root?
Root
If
will be the time.
no, I understand, but what? Because we want to make sure that we create a balanced tree, right? Otherwise, it won't be efficient.
You think of right. Let's think of binary search tree as balance for now. Okay,
Okay.
that it is internally balancing. You're using red black tree or AVL tree. It's balancing internally.
Sandeep, we can use linked list for this.
Okay, so people will keep on adding tasks. By the way, so how would you keep this linked list ordered? How should this look like?
Like the next stack, we sorting the list and the putting the list linked list node is the based on the their sorting time period. Like this is the
Okay,
maybe the
so every time somebody is adding a task, you will sort it and keep it in the list.
yeah, that is difficult. Yes.
So one of the strategies could be, okay, strategies could be like one strategy. It's not, there's nothing wrong in it. So right. So right, strategy number one. Okay, whenever a task is added, sort the list of tasks. Okay. So what is the complexity of this one? On every task, n times log of n, right? Okay. So every task has to go through this one. So if you have to add n task or to you the every time the sorting is happening, so it'll be approximately this one. Sorting takes n log n, and we have n tasks. So on an average, it'll come out to be this one.
Yeah.
Okay.
Okay. Yeah.
So not a bad idea, but yes, it is a little slower. Okay, can we make it faster? This is a strategy one, and this is strategy two. Okay, any other strategy you would recommend?
Sir, can you explain again why are we using binary search tree for this?
No, I mean, we are just talking about all sorts of approach. Okay, I did not say, I did not reveal the answer yet. Okay, I did
Okay.
not reveal the answer. Basic question is, lots of people keep on scheduling the task, and your executor has to pick the task which has the smallest start time, and then you have to execute it, and that's about it. Okay. You have to execute it and delete it from the task list, and then pick the next task, which is within 1 second of current time, and then delete that one, and then you keep on doing it. So on one end, your users are adding the task, and you are continuously deleting the tasks based on the time. Okay. So first strategy was that whenever tasks get added, we maintain a list, we sort the list, and that's it. This strategy, by the way, just to give you an idea. So I have seen like multiple schedulers in past. One of them was something like Java Quartz scheduler. Okay. That one uses this strategy. Okay. So it basically keeps everything in a database, and whenever tasks are getting, it keeps on inserting and the index keep on getting prepared. But it's not necessarily sorting the entire list. It's leaving the sorting or index to be updated to the database, because database is smart. It uses binary search tree to keep on doing that.
And the one more thing, strategy one, can we use doubly linked list? That will be the faster we know the previous and the next node. Then
But why? But why can't you just keep a list? Why do you need to know the next task? The only advantage you are having is that if you delete the current task, you can go to the next one easily. That's why you are keeping a linked list. But
linked list.
every time a new task is coming in, right? Okay. Okay. So so strategy one is linked list. Okay. Linked list. Okay. Right. So when a task, okay, those who are not aware about linked list, it's basically kind of a list. This is first element. Okay. You keep a pointer to the next element. Okay. And this is, let's say, value. This is 1, this is 2, and this also contains a pointer, and like that. So the way you usually create a list is by creating a class called node. Okay. And you'll just say that, all right. And so this is how it would look like, right? So it'll look like self.value. Okay. And let's say value, self.value equals value. And I'm saying self.next equals to none. Okay. And then you can basically keep on, right? This is a node, and you basically linked list is nothing but a node which is pointing to other nodes. That's it. Okay. So you can basically keep this way. Okay. So whenever a new task comes in, you go over this list and then find a place where to insert. And when you basically delete this one, you start pointing to this one as head. Earlier head will be pointing to this one, then you'll start pointing to this one, and like that. So you keep on moving in that list. Now tell me, in such kind of list, right? Right. What is the order of inserting a task? For inserting a task, you will go from one to next, next, and next. So you'll, right? So order of n, correct?
Searching, yeah.
And okay, and deletion,
Same order of n.
order of one, right? Right? You basically will just take the head and that's it. So inserting a task is order of n, right? You keep on searching and then you delete. So here, right? The insertion is taking, what is the order of insertion? N log n.
Log in.
Okay. And deletion, like finding the minimum, finding the smallest element. Find, we'll just call, instead of saying find min, is going to take how much time? Find min and delete. Find min and delete. Okay. So it'll first, when you have this kind of a list, right? Find min is going to take how much time? Let me see if I can just break it. So basically there are 3 operations: find min, delete. Okay. So find min is taking how much time here? It's a list sorted. So find min is log n, and delete is how much?
Omega n. Log
N
log
log n. N log n.
Why?
Why? Because you have to sort the data, right? No, order of n, sorry. Because data is already sorted.
Already sorted away.
So order of n. Correct?
Yeah.
So you have to shift all the values to the left, because it's a list. If you delete anything, everything moves a step ahead. Okay. So the strategy one, this is strategy one, is basically, to insert, you have to, every time you insert, you basically have to sort, and find min basically is log n, and delete is order of n. Okay. The second strategy is that we are keeping a linked list. Basically, each element is keeping a track of the next one. So whenever somebody is inserting, you go from left to right, searching, searching, searching. And the moment you find a good place to insert, you insert there. And so it will take order of n, and deletion is taking order of 1. Is everybody okay with these two strategies so far? Now, strategy number 3. Anybody?
Sandeep, why the strategy one find min is log n? I didn't understand because it is already sorted and first element is the minimum, right? Then why we need log n?
That's a good point. Correct. You're right. You don't need this is correct. You're right. So this is order of 1. But when you're deleting it, all the elements have to be shifted. So
that is correct. That is
yeah. Okay. Perfect. Very good. Very good point. So insertion is taking n log n, and finding min is 1, and deletion is taking order of n. Now, so strategy number 2, insertion of a task is taking order of n, deletion is 1. So I would actually just prefer this one as well. But this one is just too slow for inserting a task. Okay. Now let's take a look at any other strategy that you guys have in mind.
So Sandeep, can we use graphs like BSTs or something like that?
Okay, let's say binary search tree. Strategy number 3, binary search tree. Okay. We'll just call it binary search tree. Okay. Now, how would this look like? Right? So insertion into binary search tree is you basically go from top down looking. So you basically travel the height, and how much is the height of a tree, of a good balanced tree, is a logarithm of elements. So log of n. Right? That's insertion. And deletion, finding the minimum, you go left, 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 left. So log of n.
Right.
Right? Good. A deletion is, by the way, order of again. Basically, these two things can happen in a single shot. Okay. Deletion again is a log n, so you can say that it's approximately log n. Okay. So out of these 3 strategies, which one seems to make sense to you right now? We had this strategy. We had this strategy. Okay. We had this strategy. Can we use a dictionary for this strategy? Anyone?
I mean, we can use dictionary, but then we will always have to sort the keys of the dictionary. So we'll always have to sort it, right?
Exactly.
So
Exactly.
every addition will require a sort. So it will be something similar to
List
the first
one.
right? Yeah.
Since the elements in a dictionary are not sorted, right? You can insert at position and delete from a position. The finding the minimum is going to be painful task. Okay. All right. Anybody else?
With this strategy to linked list looks to be more efficient.
Yeah, but inserting a task is order of n.
Okay.
Out of these two, strategy 3 still is better. Log n, log n.
Implement of the linked list is also difficult.
Yeah. I mean, let's imagine that you have all the things in place.
Linked list is way easier than BST. at least in
Yeah,
implementation
always,
wise.
And
always
anything that we do not know well looks hard. Okay, that you can admit.
Yes.
that is correct.
Okay. So I like when I'm talking to kids, right? Instead of figuring out like what are their weaknesses, asking them which what are their weaknesses, instead of asking them, I ask them, which topic do you think is hardest? Okay. So they'll usually choose the topic which they don't understand as the hardest. Okay. Anyway, so I think it's let's just so say that you have library of all the algorithms. Most of the library, like if you go to Java's library, they have binary search, and all these data structures and algorithms are available as part of collections. There is some in Java. There is a collection. In case of Python also, you have all these algorithms available. Okay, so once you know it, you don't have to implement it. You just need to know when to use what. Okay, and I can tell you confidently that in industry, you would not be implementing these things. Most likely, you'll just be using it. Okay, now question is that how do you? Question to all of you is that so far out of these, it's very clear that strategy 3 seems to be winning, correct? Because here it's order of n, so you lost it here. Order of n, we lost it here. So this one is the only log n, right? Now, question is, do you have something else in mind? Okay. Anybody else? Can we do better than binary search tree? Everybody okay, right? The insertion is going to be log n and deletion and find min is going to be log n.
Arbitrary, like red black tree.
It's the
It's
same thing.
already
BST is red black tree. Okay. I mean BST, red black, or AVL. Basically, AVL and red black are basically different implementations of binary search tree only. Okay. So, all right. Now, question is there anything that you have in mind? Okay. Any other strategy? Task is simple. People will keep on calling your API to schedule task. Schedule task will have the command line, and it'll have the start time. People, and you'll have to keep on adding it, and you have to have two things. One is something that is updating your data structure, add and delete, and then you need to have the scheduler, which will keep on sleeping for some time, waking up, checking the minimum task, and then removing it, executing it, then again going to sleep, waiting till the next task to execute, and then keep on executing. So it'll have two parts to it. And yeah, so basically the schedule part will keep on searching for the next task, and remaining part, the remaining API that you give to your customers will keep on adding, deleting, or managing the tasks. Okay. Now question is, can we do better than BST? Any other?
Can we use some algorithms like shortest path algorithm in graph search or something like that?
But you need to arrange your data in certain form, right?
Yeah.
So it's about arranging your data. Like when people are inserting, it should be quick, and when people are when scheduler is searching, it need to be fast. Okay.
like one more case. If we like the 24 hours a day, that we have the 24 queue or 24 stack, then
Mm-hmm.
we don't need, if the restrict for the user key only the 1 hour cron job, we pick that
Mm-hmm.
or we put that, Then the 24 stack, we don't need to the sorting or searching. That the
Okay.
every hour have the own
Okay.
stack or own queue.
So let's say the task need to be the minimal time is based on seconds.
That is different. Yeah, that's why.
Okay.
The
Every day has a second, say, for example. And what you do is, let's say you create a list. Create a list of let's say 64. How many how many tasks are there in usual? Okay. So create a list of how many seconds are there?
for 1 hour.
So 24 hours, minutes,
86,400.
right? So create a list of these many elements, okay? And basically just keep, right? For each day, you have to have these elements. So if let's say there are 10 days, so you create list of lists for 10 days, okay? Or 100 days, then you can create this, and then basically just keep checking for each second if it is existing or not. Now this is going to be crazy. If you are, let's say, aiming for say 3 years, okay, then it'll have these many elements. Okay. But let's just note down the insertion deletion. Insertion is taking how much time in this? Order of 1. Find is taking order of 1, and deletion is taking order of 1, right? Okay. Looks cool, right? It just have how many elements? 3. And if I just create an element, right? Okay. So I'll just create this array. Okay. All right. So does it give the size? There's a size of, right? Size.
There is
Yeah.
There's info, right? No.
There is something else. There is something else. Find the size. They changed the size of operator. Okay. Size of in Python. Okay. How to determine size of an object in Python? System.get size. Okay. We'll say import system and system.get size of A. Okay. So these many elements. Okay, so it's going to be pretty big. All right, so this million. So 691 megabytes, right? So 6 times of this, I think 8 times. Yeah, 8 times. Okay, so eight bits, these many bits, I think. These many. No, it'll be 8 bytes. Yeah, this will be 8 bytes. Got it? So the challenge that you see here is that that's going to just be too memory intensive, but it's a good strategy. Anybody else? So this is
Can we
probably
use hash tables, Sandeep, like a separate hash table for maybe we can use some hash algorithm which can generate a unique value based on the minutes, hours, seconds, and days, and then we can just use that hashing to search and get the element.
Okay. You are okay. Hashing could be like you can create, right? We can create an extension of the previous strategy. Okay, let's say strategy number 5. what we could do is we can maintain per 10-minute window, 10 minutes window tasks. And basically in each array, so you'll have 10 minute, 10 minute, 10 minute, and then we keep on searching in only the 10 minutes window. So it becomes a little faster.
Yeah.
Hey, Sandeep, you know what you just said, right? Maintaining an hash, right? We can have epoch hash we create a epoch hash, right? And every
Yeah,
time
the
we just
same thing as that one, right? So by creating an epoch hash, you are basically creating a window, a group of say elements together, and then you can essentially keep things like that, right? But again,
yeah. So
there is a big risk there that if whatever hash strategy you choose, what if all tasks end up in that hash?
no, if we create epoch based time, right? It will be unique for every second.
Yes.
Right? So we can create, so every time a task is added, we'll get that second and we'll put that in the epoch. And then every time we will search every second in the loop to get that hash from there. So if there is a task there, it will execute. If there's not there, then we'll go to the next one and so on.
Yeah,
I mean,
yeah. So internally, what will hash table do to optimize the space? It will basically still will be a big space consumed by hash table. Okay. And
no, it won't be big table, right? Because it will have only a number of elements which are there, which were inserted, right? So, for example, every time you insert, you create the epoch hash and insert it in the hash table.
But epoch hash internally would be converted into number, and dictionary will be consuming a lot of space anyway. Dictionary will consume a lot of space, right? And how would you search that? How would you search that? You will take an epoch and search in the dictionary?
Yeah, it will be just order of one, right?
No, now if you ended up missing a particular epoch and you wake up now, so you will have, let's say your job got killed and some task was supposed to be executed one epoch earlier, right? Now you're only looking for the current epoch, so you will miss this task, isn't it? Got it? And second
isn't that happen in cron? That is what happened in cron also, right? I mean, for example,
but you have to keep on checking every epoch.
Yeah.
Every epoch, right? You have to keep checking on every epoch.
Every second. Yep.
Yeah. On every second, so you have to keep on checking, right? General strategy usually with schedulers is that you basically find out what is the smallest next earliest task to execute, and if it is like 5 minutes later, then sleep for 5 minutes, wake up after 5 minutes, and then do the task. Okay. So essentially for every one is maintaining this dictionary is going to be similar to this, a little more optimum than this, a little more, not much. Okay. Second is that it is going to be slower in general. As in, it will consume a lot of CPU. Yeah.
Yeah,
okay.
But just thinking out loud, if we wait for that much of time, we see which is the lowest one, and then we wait for that much time. If there is an insertion of task, right, while we are waiting. So, for example, next task is like after 3 hours, we wait for 3 hours, sleep for 3 hours.
So whenever the insert method gets called, you actually wake up your scheduler. Got it?
Yeah.
You basically
Yep.
You essentially wake up your scheduler, hey, check again your data set and don't sleep. And all right, good. Okay, so this is similar to the first strategy. Okay, I'll just put it here. Okay, use a dictionary for a more optimum time. Okay, basically we created a optimum space, not time. Okay, we created a list, you created a dictionary. That's all, based on epoch. Okay, now what else we could do?
Can we use something like converting those in a bits, like 0 and 1, like for 24 hours we can have 24 bits? Similarly, for 30 days, we can have bitmap,
Hmm.
and then based on the values of one from each of those array, we can identify that what exactly the timing is.
Right. Yeah, okay. So it's the same thing, right? As creating a list of elements but based on epoch.
It will be fixed like for 24 hours you have 24 bits, for 30 days you have 30 bits, then for 12 months you have 12 bits. It is fixed for every count entry, right?
But
So
number
whenever a
of
count
elements,
entry,
how many elements will be there in this?
so we need to for every element we need to first convert it into the bits, and corresponding bits need to be on.
Yes, yes. And basically, how many elements are going to be there? Think of this. I
In the
think
list you mean, right?
basically you can optimize it a bit using vectorization probably, but I'm not sure how to do that. Okay, I'm not sure. I need to think about it. But yeah. All right. All right. Good. Very good strategies. Any other thing that is coming to your mind? So basically, we discussed multiple strategies. Number one is whenever task is added, we sort the list and we maintain a sorted list and do that. Second is using a linked list whereby we keep on deleting the element from the top so that it doesn't, by keeping the pointer to the next element, we kind of optimize on the deletion one. Okay. Next is the binary search tree. Next strategy is this one. This actually is not at all possible because this one is going to take how much memory you can see. 3, 6, and this. But at the same time, if we are going with the epoch way, the way Subodh is suggesting, that can be worked out. Okay. And similarly, you can try to create a window, right? Now is the time for the actual data structure that is called min heap. Okay. So min heap is very much like a binary search tree. Okay. Let's talk about min heap. Okay. Now min heap is again like a tree. It's like a tree. Okay. It's like a tree. Okay. So when you insert an element in it, okay, so the parent node has to be the smallest number. We call it min heap. Min heap means top value is always the smallest. Okay, like for example, if I insert 67, right now 67 is the top node. Okay, then I add, let's say, 89. Okay. So 89 is bigger. Okay. So in case of min heap, both left and right childrens are bigger than the parent. Okay. All right. Both left and right are bigger than the parent. Okay. So you can see, right? Now 7. So when I inserted 7, 7 basically was swapped at the top. You see that? 7 was inserted, then it got swapped with the top, and that's it. So you can very clearly see internally the way it's doing is it's basically keeping the elements like this. First element came in, okay, right? And let's say I'll again do that. Let's say 34, okay, 45, 54, okay, and 45. Okay. So you can see it has basically capped it like this: 34, 54, and 45, right? The moment a new number which is smaller than this comes in, what it does is it will basically swap it with the parent and will keep on moving it up the ladder until the smallest value reaches the top. Okay. So let's say I insert, let's say, for now, let me just insert 40. Okay. You can see 40 gets swapped here, Now 40 is, so 34 is smaller than 40 and 45. 40 is smaller than 54. And the way it's keeping is, this tree is like a list inside. Okay. So it's keeping the tree like inside like this. So there is 34, left, right, and then again next and next. So like that. Now let me again move to the next value. So let's say I have 56. 56 can be added at the bottom. Okay. And then if I add, let's say 20 right now, it will add at the bottom and then it'll keep on swapping with the parent. Okay. You see that? So we add the element at the bottom and then we bubble it up to the top. This is called min heap data structure. So every time we are adding the elements, the smallest value is bubbling up. And every parent node is smaller than both the children. Okay. 40 is smaller than 54 and 56. 34 is smaller than 45 and so on. Now, if I delete 20, what it will do is it will pick up one of the smaller values, either this or this, and move. Which one is small? 34 or 40? 34, right? So it will basically swap 34 to the top. Okay. So let's say I delete, I remove smallest 20. So you can see basically 34 bubbled up. Okay. Now if I remove 34 now, the remove is smallest. Okay. So you can see 40 bubbled up. And all right. So whenever you're removing, it's moving one of the elements from the bottom to the top, and then it basically keep on swapping values until the smallest element has reached the top. Okay. Everybody okay with this?
That means if we removing the element, this shifted the right shift to left shift to the every element in the list.
Yes, yes. In
Then
the
rearrange the graph based on
yes,
the indexing of the list.
yes. And basically the graph is mostly filled from the left to right.
Left is the first. And this is the balance graph. Until the left node is not balanced, it doesn't goes to the right side. First is the balance to the right left side, then go
Left.
for the right side.
Yes. Okay.
That doesn't mean ki number is bigger or lower. This is the balancing the graph.
Yes. So like for example, if I'm adding say 45 and then I'm adding 23. Okay. Now 23 is at the top, 45. Now if I add a next element, say 30, okay, it is added like this. Now if I add a number which is, let's say, which is any number, so it's going to insert at the leftmost and then keep on swapping it if the parent is smaller, parent is bigger. Okay. Let's say I add here 67. It'll keep on, it'll add here and then it'll basically. Okay. So essentially it's very simple. Every value's parent exists at divide by 2 position, right? 5 divided by 4, 5 divided by 2 is how much? 2. Correct? So 64's parent is 45. 45's parent is, this is just 2 divided by 2 is 2 divided by 2 is 1. So this is the parent. Correct? So any number 4 divided by 2. Basically, we keep on filling from the left to right so that essentially we don't have to maintain the tree. Internally, it's just a list. How to find the parent? Take the element, divide by 2, you will find the parent. Okay. Is everybody okay with it so far? No?
Yes.
Okay. So this is called min heap. Quality of min heap is, okay, right? Order of insertion. Like, what is the order of inserting? How much time? Insertion is insertion's complexity. When you are inserting, it basically puts it at the top and then bubbles up. So it's order of log n. Okay. In any tree, if it is well balanced, if it has n number of nodes, the height of the tree is going to be log of n. Correct? Because on every level, the number of elements are growing up, correct? So here it became 1 plus 2, 1 plus 2 plus, so at every node, whatever is the height, the total number of node that will be there up to here will be 2 to the power h minus 1. Okay, it'll be like this. So whatever is the height, it'll be 2 to the power h minus 1. If height is, so how much will be there? 1 plus 2 to the power n. Okay, so 2 to the power 0 plus 2 to the power n, like that, right? So coming back to it, how should I put it? Okay, so it will be 2 to the power height minus 1. Total number of nodes. So if height is 1, how many nodes are there till here? 1. Okay. So 2 to the power 1 minus 1 is 1. Now 2 to the power 2 minus 1 is 3. So up to here, 3 nodes. Okay. And up to, let's say there are these 2 more nodes. So 1, 2, 3, 4, 5, 6, 7. So 2 to the power 3 minus 1. Okay. So this is height. So 2 to the power height minus 1. These many nodes are there. If the tree is of height h, these many nodes will be there. Correct? If there are total number of n nodes, how much is the height? H equal to log of n. Basically, that's the definition of log, right? So height is going to be logarithm. All right. So log of total nodes. Okay. So in case of min heap, insertion takes how much time? Log of n, correct? And finding min is going to take order of 1.
Order of 1 bit.
Right? And deletion, order of log. Okay? Because it's going to bubble up. So the power of min heap is that okay. So min heap is slightly better. Min heap is slightly better than BST. Correct? So insertion is taking log n. Find min, here it was taking log n, but here it's taking 1. Because minimum is always at the top. Okay? Minimum is always at the top. And in case of a scheduler, finding minimum is a very common operation. Okay. Therefore, for scheduler, always the min heap is the best strategy. Are you guys okay with this? No?
Yes.
Okay. So in case of Python, right, you can basically just use the heap queue. Okay. And so you can basically just keep on, let's say, using this. Okay. So this is, let me just show you. If you have x equal to 3, 4, 5, 1, 2, 8, 9, right? And you say heapify x, okay? And okay, so right, so it will basically sort it such that the smallest value is at the top, and so on. It's not perfect sorting, but the parent of 3 is what? 1, 2, 3, 4, 5. 5 by 2 is this. Okay. Yeah, parent of 3 is 2. Parent of 3 is 2. Okay. So yeah. All right. So essentially, essentially it is how should I say? So it has strategically kept the parent of every child to be this smaller than the child, and that's it. So here you can simply say x0 just to find out what is at the top. Okay, and that's pretty simple. And then you can also say heap pop. You can say heap q dot heap pop, and then it basically would delete the element at the top, and will keep on doing that one at a time. Okay, so you can see now the moment you say, yeah, so we deleted one, and the moment we deleted 1, 2 came at the top, and 3 also bubbled up, and so on. So it keeps on doing that work. Okay, so you can use the predefined libraries, and for binary search tree, for dictionary, for all of these data structure, Python has good library. Okay, so you can take a look at the heap. Okay, all right. Okay, all right. So I hope this made sense to you. There are many use cases of heap. One of the use cases in when you are searching for smallest path. Okay, the way it works is that every step you find all the positions. Okay, all the positions where you can go from here, current position, to the target. Whatever steps you can take, you take all the list, find their distance from the target, and then take the smallest value of it, put it in a heap. From that you pick the smallest, and then from there you take the next step, find all of the values, again put it in the heap. From that you pick the smallest, and that's it. So this algorithm is called A star. Okay, so you can take a look at A star visualization. Okay, so what it does is it basically lets you, let's say you are here, okay, and you want to go there, correct? Now what it does is it will, where all can you go from here? You can go to any of these rectangles, right? Okay, I'll just clear this. Okay, so how do I clear? Okay, so let's say from here to here you have to go. Okay, you have to find the shortest path from here to here. Okay, so what will you do? You are here, right? First, you will find all the positions that you can move from here. How many such positions? 3, 6, 8. Total 8 positions you can go, correct? Now, out of these, which one is closest to your target? This one. Then second closest, this one, this one. So you would like to order it such that the smallest value is at the top, correct? So you will try, next time you will try this location. Where all can you go from here? Here, here, here. Now, out of all the points, right now, these things are also lying in the queue where you want to try these positions. And these 3 values have been added. And so what you'll do is you'll basically keep all of the next trials in a heap and keep on picking the shortest one and then keep trying that. So it's basically a greedy strategy. Pick the one which is closest to your target and And if that doesn't work out, then you try the next one, then you try the next one. Like if you say, let's say this one is not working out. Okay. Let's say I've created a kind of a wall between these points. Okay. And how do you make it work? Okay. Start and wall. And these are visited. I'm going to just say start. Why it's not working? Don't tell me it won't work. Oh, I have to select an algorithm. Okay, I'll just take A star and not like this. Okay. Oh, nice. They have a lot of interesting one. Okay, so I will just show you first one. Okay, speed, slow, slow. Okay, I'll say start. It find it, right? So at every point of time, it is. Can you further slow it down? It's pretty simple. At every position, it's first exploring all the location. Okay. Can't I just do it stepwise? Is there a way? Okay. So it's exploring all these locations and then it's finding that, right? Okay. Now here, if you basically have things like this, okay, then this greedy strategy will not work that well, okay, but it will work. Okay, so I've created walls between them. So it's going to give it first try till here. And when it can't go here, then it will start trying others. And then basically, then it'll try the last one here. This will be the last path. And then it'll come back. Okay, so let's just see. Okay, you can see that it tries that one first, which is basically closest to the target. And it basically then comes back, right? So it's just trying all of those values which are closer to the target, and then, right, it's just moving in all directions now. Okay. Got it? So it's greedy. It's greedy because it tries to go from here to this direction first, because that's shortest distance, and then it tries the other distances. So at every point of time, it's adding the new points, the new explored points to the list, ordering them based on the distance from the target, and then picking the shortest one next time and then exploring it, and then it'll keep on doing that. Okay. Is this clear to everybody? No.
Yes.
Looks like I put everybody.
Yes.
Yeah, I did. Yes.
Prasant, okay. Prasant, you got your answer to your question? How deletion will be order of 1 from the linked list? Sorry, I did not see the question. Okay, so this is another use case of heap. Okay, it maintains a priority queue. It basically picks up all the points that it has explored and picks the next one in the priority. Okay. All right.
Sandeep, one question: heap also used for the threading, or the like in the Linux we create a thread. Then how to internally they also create the heap or something?
Ignore that. Okay. Heap is a continuous memory given to your program. And this heap is basically misnomer there, right? This is a because it's kind of keeping everything in a continuous tree, a list. That's why it's called heap. Okay. But these two things are different. The heap memory that your program allocates to your software is different from this heap tree. Okay. So the priority queue or heap, min heap, there is something called max heap as well, but you can simply just put minus sign in front of all the values such that max value will come to the beginning. Okay. So the strategy remains the same. Okay. Now, so this was heap. So we talked about AVL trees, binary search tree. We talked about different strategies for scheduler, and basically the min heap turns out to be more efficient than the BST. Okay. Is it clear, Subodh? Everyone?
Yes.
So the difference between min heap and BST is just that we are putting the minimum value on top instead of.
Yeah. In case of binary search tree, left-hand side is small and right-hand side is big, and top one is midway. And in case of in case of min heap, parent is smaller than both the children. Okay. There is no order in the children. The only order is the left-hand side of the tree should be full always. Okay. Right-hand side can be empty. Got it? So like if you look at any any heap, let's say this heap is there and we did heapify, right? So this actually looks like this. One is at the top, 2 and 5. Okay. Then 4, 3, 8, 9. Got it? So one element, 2 elements, 4 elements. Okay. If let's say there were minus 30 value here. Okay. So then the heap will look like this. The heap will look like this. Minus 30, 1, 5. So first element is the top node. Next two elements are their children. And then next two elements are their children. Okay. So finding a parent is pretty easy. Just divide their index by 2. You will end up here. Okay. Divide their index by 1. You'll end up here. Okay. So you can clearly see, right? The top node will be 1 element, then next one will be 2 elements, then 4 elements, then 8 elements, like that. Okay. So if you divide by 8, you will be divide 8 any of these elements by 2, you will end up somewhere here. Okay. So you'll basically always if you divide element's position by 2, you'll basically be you can see it here, right? 1, 2, 3, 1, 2, 3, 4, 5, like that. Okay. Or let me clear it out. So first element in the list, second element, third element, fourth element, fifth element, sixth element, seventh element, eighth element, ninth element, 10th element, 11. So you can see. And 12th element, 13. In case of binary search tree, this thing is not right. If let's say this is not a heap, a valid heap. Okay. If we have this kind of a tree, this is not a valid heap. Okay. Because all the elements have to be towards left. All right. I hope you got the idea. In
Yes, sir.
addition to what you said, there are a couple of more things. All right. So that's good enough. All right. Okay. Now, So these were like balanced trees, and we talked about these trees. Okay. And we also talked about going through the trees. Okay. Like how do you traverse the tree? Okay. So let me now talk about traversal of trees. Okay. There are two ways to go through a tree. One is called depth first, and second is called breadth first. Okay. All right. So depth first, as in, let's say you have a tree. Okay. So let's say you have a tree. Okay. Let's show you the tree A, B, and C. Okay. So when we say depth first, what we mean is that we should finish the depth first. So we keep on going here, and it'll print B, C, A. Okay. And if we say breadth first, what we are going to do is we are going to this is depth first. You basically try to look in the tree. Okay. If you say breadth first, we call it BFS. Breadth first search means you go down here, try these, then you try these, and so on. Okay. So A, B, C, D, E, F, G. Let's say this is your tree. It has how many nodes? 4 nodes, 2, and this. So total 7 nodes are there. When you do depth first, it's pretty simple. You start with, let's say, going down, down, down. Then you print this. Okay. So you're basically printing these elements. Okay. Let's say depth first printing. How would it look like? You'll start from here. You'll go left. Let's say you're going depth first, right? First go left. Okay. So you went left, right? Then came back. Then again printed E. Then came back and printed B. Okay. And then and so on. So basically keep on going to the bottom. Okay. So this is called depth first traversal. The other one is BFS, breadth first search. What do you do in breadth first search? First, look here at the top, then look at B and C. Okay. Then look at D, E, F, G. Okay, like that. So this is basically the ways you travel, the ways you travel. Okay, let's say visualization. Okay. All right. So how should I show you? Okay, can I? Okay. Okay, there are quite a few things to teach there. DFS visualization for tree. Okay. Will it be? They don't have like they don't have for a tree. Anyway, I think depth first and breadth first is probably more common with respect to a graph. Okay, we'll talk about the graph, don't worry. All right. So you can see that this is depth first traversal. You started here. Okay. And you went one. Okay. So you kept on, no, that is not here. Yeah. So depth first travels, this is what I meant. So when you say this is your tree and you basically want to, it's too much of ads here. Depth first traversal of the tree will be like in order. If you start here, keep on going. In order means print the center first and then left and right. And then you come back here, you print 2, then 5, then you come back here, then you print 1 and 3. So you basically went till the bottom and then printed. Okay. So this is called depth first traversal. You go down till the bottom and then do that. While the breadth first traversal is this. Okay. I just want to show you for tree. I just want to show you one example. Breadth first search is basically searching for the nodes breadth first manner. If you have to print the label of every node, like every node, whatever nodes you encounter, every label whatever you encounter, then you use the breadth first search. Okay, we'll talk about this very soon. All right. I hope this is clear to all. So we kind of covered primarily the min heap and the various strategies for the algorithm, for the tree algorithms mostly. Okay. So yeah, any questions as of now?
Sandeep, I need to go through this today's video once again to get some doubts.
All right. Anything else, everyone? No questions? Okay, then. See you tomorrow at the same time. Have a good day. Thank you, everyone. Have a good day.
Thank you.